lecture video 1 for week 2 of our remote learning. Please download notes 3 if you haven't already. I just want to remind you that there will be another Google form on Wednesday for you to fill in. And you have a couple homework assignments. You'll have thermo web labs to do, but you only have to do 2 questions per web lab. You can do 3, but only 2 are required. And then you'll have another group quiz. Please review homework 15 answer key. There were some, number 7 in particular, a lot of people got wrong, so please check that one. Okay, all right. Little joke for you if you want to pause anytime during the video to read the jokes, etc. Please do so. All right, so thermodynamics is the area of chemistry that deals with energy relationships. Chemical reactions always involve changes in enthalpy, which is heat, and changes in entropy, which is randomness. Hopefully entropy is something that you've heard before. And I wish I was with you to talk to you about this. It's a really interesting topic. So, okay, turn off the video. Okay, so entropy and heat together help us decide if a reaction is going to be spontaneous or not. So let's review a little bit. The first law of thermodynamics, energy is conserved, so it's not created or destroyed. Typically in chemistry, we're thinking about heat energy. Now, we know that energy can be transferred or converted to different forms, but the total energy in the universe remains constant. Okay, so this goes along with spontaneous processes because of changes in heat. A spontaneous process is one that proceeds without any outside assistance. So, for example, water flowing downhill. Okay, non-spontaneous is water flowing uphill. So you can see with the picture there, we have a skier going downhill. That's spontaneous. It is not spontaneous for the skier to go uphill. By the way, this PowerPoint is based on slides that I did for AP Chemistry. It generally goes with chapter 18 in your textbook, so if anything seems confusing, you can go back to your textbook. But yes, I edited these from my AP Chemistry class last year. Okay, another example of a spontaneous process would be a gas expanding to fill a flask. Okay, so for example, we have 2 gases here, one gas in part A, an empty flask in part B. When you turn the stopcock, the gas will flow in between and fill both of them with an equal amount of pressure, and that process is spontaneous. Okay, non-spontaneous would be the gas compressing to go back into flask A. We would not expect that to happen. Okay, now spontaneity does not determine the speed or the rate of reactions. Some spontaneous reactions are fast, some are slow, but either way, a spontaneous reaction will happen on its own without any additional assistance. Okay, so entropy is defined as the arrangement of molecules and their movement, which is their randomness. Okay, in the universe, entropy is increasing. The change in the entropy, just like change in temperatures, the final minus initial, we use the S as our abbreviation for entropy. Now, if we think about, for example, a sodium chloride crystal, very highly structured, very evenly spaced particles. If we dissolve this in water, the particles will split up. Obviously, way more random to have it in an aqueous solution than to be a solid. So in this process, entropy is increasing. So the delta S for this dissolving process, we would expect to be positive because entropy is increasing. Okay, another example, water, solid water, so ice, melting into liquid water. In solid water, we have a very organized system of molecules. That also leads to the density differences between solid and liquid, and the fact that snowflakes can form into these beautiful 6-sided shapes. Water is much more disorganized, it's much more random. So when solid turns to liquid, we have a delta S of 22 joules per mole Kelvin. So entropy has increased when water melts. So just take a moment and decide what goes in between these two molecules, either greater than or less than. So pause the video. Okay, here's the answer. All right, the randomness of the liquid water is greater than the randomness of the solid water. Or in other words, the solid water has less randomness. It's more organized than the liquid water. All right, now the second law of thermodynamics says that for any spontaneous process, the entropy increases. We have a positive delta S. Okay, in other words, the state of entropy for the entire universe as an isolated system will always increase over time. So the disorderliness of the universe is always increasing. I'd like you to pause this video and watch this other video. I will post this along with everything else. Hopefully that video helped. Here is another version of the same video. If we think about two molecules of gas in a flask, you can see the stopcock is closed. If we open this, we have a few different possibilities for the gas. We could have one in each flask, opposite gases in the opposite flasks, two on one side, two on the other side. Each of these is called a microstate. Okay. Now, if we think about 2 moles of gas, there's almost no chance that all the gas molecules will be on the left or on the right. Mostly they're going to be spread out and mixed up together. So each of those is called a microstate. Okay. Now, someone who worked on these microstate ideas was Boltzmann. I have a picture of Boltzmann. Oh, here's his formula first. W is a number of microstates. Oh, that's not Boltzmann. That's the dog Bolt. Okay, here he is. There he is. Okay, so Boltzmann is also famous for the Maxwell-Boltzmann distribution. We saw this when we talked about gas speeds. So if we think about microstates, how many places that gases could be, if the gas is moving slower, like with this purple peak, there are fewer microstates. So more of the gases are going to be within a smaller distribution of speeds. If the gases are moving faster, there is a much wider distribution of speeds. So this is a very classic Maxwell-Boltzmann distribution. The faster the speed here, the more microstates we have. The more possibilities for speeds that are possible. Okay, in other words, entropy is a measure of how many microstates are associated with a particular macroscopic state. Okay, so let's think about a couple of these. So pause the video and think about how entropy changes when volume increases and how entropy changes when temperature increases. All right, did you fill it out? Here's the answers. Okay, when volume increases, entropy increases. When temperature increases, entropy increases. So if the volume is bigger, there are more places for a gas to be. So there are more microstates. When temperature increases, we know that speed of a gas will increase. That means that entropy increases because the gases will be more disorderly. Okay, here's another one to think about. So pause the video and think about this question. Here's the answer. Entropy is increasing from left to right. We have an increasing number of microstates. We know that ice is more orderly than liquid water, and liquid water is more orderly than water vapor. Okay, in general, entropy increases when liquids or solid becomes gases, which is just what we saw in the previous slide. Okay, Okay, so liquid turning to gas or solid becoming a gas, that would increase your entropy. Okay, when solids become liquids or solutions, in other words, when something becomes dissolved, then that will increase the entropy. Okay, when the number of gas molecules increases during a chemical reaction, again, there's more disorder when the number of gas molecules increases, so entropy would also increase. All right, and here's a little joke to conclude video 1. I will see you in the next video.